Climate researcher Dr. Antonella Vecchia analyses 40 years of Naples temperature records and discovers something that defies atmospheric science. Urban heat island effects should raise city temperatures 2 to 3 degrees Celsius above surrounding areas. Instead, Naples registers 8 to 12 degrees Celsius higher than meteorological models predict. Cities do not generate this much excess heat without an external energy source. Naples is being heated from below by thermal systems that overwhelm normal urban activity. Satellite thermal analysis confirms underground heat generation covering 150 square kilometers. What this temperature database revealed has rewritten volcanic threat assessment across Europe. Campi Flegrei's 5,000 tons of carbon dioxide every day represent cooling exhaust from underground thermal systems that have turned Naples into a city-sized pressure cooker, where hundreds of thousands of residents live above a slow, systematic build-up of explosive steam energy on geological timescales. Climate research accidentally uncovered evidence of a hidden threat beneath an entire city. Naples has been heating itself for decades, while residents assumed it was normal urban development. If temperature records can reveal underground explosive preparation, the question becomes what happens when those thermal signatures cross the point where pressurized water flashes into destructive steam. 39,000 years ago, Campi Flegrei unleashed the most cataclysmic volcanic eruption in European history. The Campanian ignimbrite explosion expelled hundreds of cubic kilometers of magma and ash, reshaping the Italian coastline and leaving behind a vast caldera that would one day cradle the city of Naples. For millennia, this region was known as the Burning Fields, a landscape that constantly released heat and gas from the earth below. Ancient civilizations built temples here, drawn to boiling lakes and steaming ground, unaware of the deeper forces still active beneath their feet. Over centuries, the caldera entered a strange rhythm, known as bradyseism. The ground slowly rose over years, then sank back again. In 1538, one of these uplift episodes produced Monte Nuovo, a new volcanic hill formed in a matter of days. In the 20th century, these movements intensified. In 1950, parts of Pozzuoli rose nearly 2 meters before subsiding. The 1970s brought another surge. Then, between 1982 and 1984, the ground lifted again by almost 2 meters, accompanied by thousands of earthquakes. 40,000 residents were evacuated as authorities feared an imminent eruption. Despite this instability, Naples continued to expand. Population growth and infrastructure spread directly over the caldera. By the time volcanologists struggled to interpret the unrest of the 1980s, a completely different field of science was uncovering a deeper and more unsettling reality. Dr. Vecchia did not study volcanoes. She studied climate. But as she examined decades of temperature data, a pattern emerged that could not be explained by traffic, buildings, or population density. Naples was far hotter than any city should be. Satellite data confirmed the anomaly. Heat was rising from below the surface across an enormous area. This was not isolated geothermal activity. It was a connected subsurface system generating energy on a massive scale. For years, scientists attributed Campi Flegrei's carbon dioxide emissions to magma slowly degassing underground. But when viewed alongside the temperature data, those emissions took on a new meaning. The gas was not simply leaking upward. It was venting pressure from an enormous hydrothermal system. Three-dimensional seismic imaging has since revealed networks of pressurized reservoirs beneath the caldera. Temperatures exceed 400 degrees Celsius in places. Water trapped under sealed rock layers heats, expands, and circulates through fractures, steadily building pressure. As this process continues, energy becomes concentrated beneath populated areas. Urban foundations, tunnels, and buried infrastructure unintentionally create pathways that could amplify the effects of a sudden release. Unlike traditional volcanic eruptions, these explosions do not require magma to reach the surface. When superheated water abruptly converts to steam, its volume expands violently in an instant. The force can fracture rock, destroy structures, and release enormous energy without warning. This is the steam explosion, and it behaves differently from anything most disaster planning accounts for. For the people living above Campi Flegrei, there may be no clear warning signs. Steam-driven events can escalate from stability to destruction in seconds. By the time strong shaking is felt, the release may already be underway. Urban systems would intensify the damage. Confined spaces could channel pressure and heat. Buildings could fail from below. Emergency response would be overwhelmed immediately. The human impact would be severe. Extreme heat and pressure cause widespread injury and structural collapse. Hospitals would face conditions far beyond standard disaster scenarios, with infrastructure damage limiting response when it is needed most. The economic consequences would extend far beyond Naples. Transportation, tourism, shipping, and regional trade would be disrupted. Ash and debris could ground air traffic across southern Europe. There is also the risk of cascading effects. Campi Flegrei lies only a few kilometers from Mount Vesuvius. Sudden pressure changes or seismic waves could influence nearby volcanic systems, increasing regional instability. Despite this, the scientific response remains cautious. Existing monitoring tools were designed to track magma movement, not large-scale hydrothermal energy build-up. Subtle steam pressurization can evade traditional detection methods. Researchers now warn that this represents a different category of volcanic hazard. It is not driven by molten rock rising toward the surface, but by heat and water accumulating below sealed layers. Dr. Vaiti's analysis shows that the thermal signal is not stable, it is increasing. The system is becoming more efficient at trapping and concentrating energy. There is no clear timeline. This process could continue quietly for decades, or it could accelerate faster than expected. Each day of gas release indicates continued heat input below the city. For the first time, surface temperature analysis offers a way to track this hidden system indirectly. Subtle changes at the surface may reflect pressure changes deep underground, but that insight comes with an uncomfortable implication. If decades of climate data already reveal this much, the future trajectory remains deeply uncertain.